Somewhere above you, right now, the sky's older than every story ever told beneath it. It looks still, stars in their slow drift, the pale edge of the moon, if it is out tonight, hanging in the dark as if it has always been there. None of it knows you are watching. None of it ever has. For almost all the time this planet has existed, there was no one here to look up and wonder what any of it meant. Try to feel the size of that. Not the number, the silence. Mountains rose and wore down to sand with no eyes to name them. Oceans filled, emptied, and filled again. Forests grew, fell, sank, and hardened into stone. For most of that history there was no mind on Earth to call any of it beautiful, or strange, or ancient. The planet didn't need us. It went on for almost its whole life without a witness who could turn the world into a story. Think about what that word means. A witness is not just something alive. Bacteria were alive for billions of years, but they were not witnesses in the way a mind is a witness. No remembered yesterday, no imagined tomorrow, no before and after held as a scene inside the self. A witness is something that can take the world in and keep it. Something that can carry a moment past the moment it happened. For nearly the whole history of this planet, nothing here could do that. Things happened, and then they passed back into rock, water, air, and time. And then, in the very last sliver of that time, so recent it barely registers, something opened its eyes. Something began to notice. Something started keeping track. That something was us. Here is the strange thing we will sit with tonight. We are not old, we are not central. By every honest measure, we arrived a moment ago and could leave just as quickly. And yet we are the only part of this story so far that has learned to tell the story back. So this is not a story about how important we are. It is something quieter than that. Tonight, we are going to walk backward through deep time, past the cities, past the ice, past the first breath, past the first rain, all the way back to a world of fire with no name. And then we will come home slowly, watching how each ancient thing, none of it meant for us, somehow made us possible anyway. We will not rush. There is no need. The story took 4.5 billion years. We have a little while. Let us begin where everything we know runs out, at the edge of the dark before the first morning. There is a problem we have to deal with before we go any further, and it is an honest one. You cannot picture 4.5 billion years. Neither can I. No one can. The human mind was built to track seasons and lifetimes, and maybe the span between a grandparent and a grandchild. Beyond that, the numbers stop behaving like time. They become marks on a page. So let's not begin with numbers. Let us use something we can feel. Imagine the entire history of Earth pressed down into a single year. One calendar. January 1st is the planet's birth, a glowing ball of molten rock. Midnight on December 31st is this exact moment. You, here, now. On that calendar, a single day is about 12.5 million years. An hour is about 500,000. A minute is a little over 8,000 years. One ordinary second is roughly 140 years. More than a human lifetime, gone in a blink. Now watch where things fall. For the first month and a half there is no life at all, just fire and cooling and rain. Life finally appears in late February or March, but it stays small, invisibly small. For month after month after month, nothing on this planet is bigger than a single cell. Spring passes that way, summer passes that way. The whole long middle of the year is life in water, stone, vents, and sediment, doing the slow work of becoming. Animals with eyes and bodies do not show up until mid-November. The dinosaurs arrive around the second week of December and vanish the day after Christmas. Flowers are recent. Grass is recent. The world that looks familiar to us is almost the newest thing here. Stay with that long middle for a moment, because it is the part we always skip. When we tell this story, we rush toward the dinosaurs and the cave painters, the parts with faces and drama. But the truth of Earth is mostly the unhurried part. Month after month of single cells, invisible, changing the planet without anything a human eye would recognize as spectacle. That is not the boring stretch before the real story. That is the real story. The longest, most enduring chapter the planet ever wrote. We are the brief, strange ending. The microbes were the book, and us, our whole species, every cave painting, every pyramid, every war, every love story, every word ever spoken, fits into the last 30 minutes of December 31st. Recorded history, all of it, is not even the final minute before midnight. Sit with that for a second. Almost everything you have ever heard of, everyone whose name survived long enough to reach you, happened in the last breath of a year that has been running since January. I do not know if that should make us feel small. Mostly, I think it makes us feel held. There is a kind of relief in it. Whatever pressed on you today, whatever felt urgent and sharp is happening in that final breath, on a planet that has seen billions of mornings without us and may keep turning long after everything we know has changed beyond recognition. So there is nothing to solve tonight, nothing to finish. We're just going to start the year over from the 1st of January and watch it unfold. The clock is running, the planet is forming, let us go and see how it was made. Start with no Earth at all. Where the planet will be, there is only a flat turning disk of dust and gas, wrapped around a young star. The dust is the remains of older stars that lived and died before our sun was lit. Many of the atoms in your body, the iron in your blood, the calcium in your bones, the carbon in your cells, were forged inside stars that exploded before this world existed, or gathered from the ancient cloud they left behind. You're not separate from this part of the story. You're made of its leftovers. The dust drifts, the dust collides, grains stick to grains, pebbles to pebbles, and slowly, over millions of years, the clumps grow heavy enough to pull others in. Gravity does the rest. What begins as specks becomes boulders, then mountains, then a small hot world, swallowing everything that crosses its path. This is the Earth, newly born, and it is nothing you would recognize. There are no oceans, no sky worth the name, no ground you could stand on. The whole surface is molten, a sea of glowing rock lit from within, churning and red. The air, if you can call it that, is thick with vaporized metal and choking gas. Asteroids fall constantly, each one striking with enough force to melt the crust all over again. The young Earth is not a landscape, it is a furnace, and it does not rest. Volcanoes do not erupt here and then fall quiet the way they do in our world. The entire surface is a kind of volcano, splitting and pouring and sealing over without pause. Lightning forks through clouds of ash that never clear. Storms rage for centuries with no living thing to shelter from them. Where molten rock meets what little water finds its way in, it flashes instantly to steam. The horizon glows. There is no blue anywhere. There is no green. There is only red and black and the white of lightning, repeating across an unimaginable stretch of time. We named this first chapter the Hadean, after the Greek underworld. It is a fair name. If you could somehow stand on that surface, you would not last a heartbeat. And the days were short, frantically short. The young Earth spun so fast that a full day lasted only about 6 hours. Sunrise, a blazing noon, and dark again, over and over, faster than any clock we know. Almost nothing survives from this time. The rock that was the Hadean has been melted, buried and recycled so many times that the planet has, in a sense, erased its own infancy. We have only a few stubborn fragments, tiny crystals called zircons, smaller than a grain of sand that somehow lasted. They are the oldest things we can hold, older than the oceans, older than the continents, and they carry a hint that surprised us, a whisper that liquid water may have existed even here, even this early in a world we once imagined as nothing but fire. We do not know for certain. The details blur at the edges. That is allowed. But the largest thing that happened in the Hadean was not slow at all. It was one catastrophe, and we owe it almost everything. A second world was out there. Roughly the size of Mars, it moved through the crowded space of the young inner solar system until its path and Earth's path could no longer stay apart. We call it Theia, and one day the two worlds met. The collision, whether direct or angled, was a planetary catastrophe. Theia and the young Earth partly melted, shattered, and mixed in the heat. Mountains turned to vapour in an instant. A vast cloud of molten rock was flung out into space, where it circled the wounded planet like a ring of fire. And then, over months, that ring began to gather itself. Gravity drew the scattered debris inward, piece by piece, until it cooled into one pale, newborn world, the moon. Look up at it tonight and understand what you're seeing. That quiet light is the scar of the most violent day in Earth's history. The disaster and the gift were the same event. And it was closer then, much closer. In those first ages the moon hung enormous in the sky, far nearer than it is now, looming over a molten world. It has been drifting away ever since, a few centimetres a year, slipping outward across billions of years, the way it still does tonight, too slowly for any of us to feel. The moon you see is already farther than the moon the dinosaurs saw, farther than the one the first humans looked up at. It is leaving, gently, and it has been leaving the whole time. Because the moon did not just hang there, decorative. It went to work, slowly, over billions of years. Its gravity reached down and took hold of Earth, first molten rock, later oceans, and began to pull, back and forth, back and forth. The tides, that steady breathing of the sea that we still set our coastlines and our calendars by. And the moon did something else, something we rarely think about. It put a brake on the spinning. That frantic 6-hour day began, almost imperceptibly, to slow. 6 hours became 12, 12 stretched towards 16, and across unimaginable time it lengthened toward the 24-hour day you live through today. The length of our mornings and evenings, the shape of a day, the arrival of night, the rhythm your body still obeys, traces back to a collision 4.5 billion years ago. We will meet the moon again before this is over, and not only as physics. When the first human minds finally appear, almost at the end of our story, the moon is already waiting for them, the brightest thing in the dark, returning on a schedule a person could learn. People counted by it before they counted by almost anything else. They marked their months by it, planted and travelled by it, told their oldest stories beneath it. Nearly every culture that ever lived put a face, a god, a warning, or a memory up there. None of them knew they were looking at the ruins of a collision that helped give them their tides, their nights, and the rhythm of their days. They only knew it was beautiful, and that it came back. But all of that is still impossibly far away. For now it is only a glowing companion in a black sky, over a planet still made of fire waiting to cool. The fire could not last forever. Nothing does. Slowly, and slow is the only speed this story knows, the surface began to give up its heat. The glow dimmed. A thin skin of solid rock formed over the molten sea, broke apart, healed, broke again. The first true ground, fragile as a scab, learning to hold. And above it, something was building in the sky. All that volcanic fury had been venting gas for ages, carbon dioxide, nitrogen and water, carried up as a vapour in enormous clouds. Comets may have added more, striking the surface and releasing their ice. The young atmosphere grew thick and heavy, swollen with water it could not yet release. Then the planet cooled past a certain line, and the rain began. Not a shower, not a storm like any you have seen. This was rain that fell for thousands of years, perhaps longer, a downpour with no season and no end. The first drops struck rock still hot enough to hiss them back into steam. But the rock kept cooling, and the rain kept falling, and slowly the water began to stay. It pooled in the low places, it ran together. The hollows filled and joined and deepened until grey water stretched from horizon to horizon. The first oceans. There is something worth pausing on here. Water became the first shelter this planet ever offered. On land, if you could even call those raw, scorched surfaces land, there was nothing gentle, no protection from the sun's radiation, no buffer against the cold of night, no stable chemistry. But beneath the surface of the new oceans, things were steadier. The water held its temperature. It softened the light. It dissolved the minerals streaming up from below and stirred them together. Where the surface world was violent and exposed, the deep water was enclosed, buffered, and full of possibility. And there is a thread here worth following, because it never really ends. That ocean was not only the first shelter, it became, in time, the inside of every living thing. Not literally the same water, not the same saltiness, not a perfect copy, but an echo. Your blood carries traces of that old marine chemistry. The fluid your cells sit in, the water that fills your eyes, the tears you cried as a child, all of it is, in a chemical sense, ocean that life learned to carry around with it. When the first creatures finally crawled onto land, hundreds of millions of years from now, they did not leave the sea behind. They took it inside and sealed it in. You are in part a small, warm ocean that learned to walk, but that is very far ahead of us tonight. Everything that mattered next would happen there, out of sight, in the deep. And while the oceans were forming above, the planet was building a second kind of shelter, this one invisible. Deep inside the Earth, the heaviest material, mostly iron, had been sinking toward the centre, gathering into a molten core. As the planet turned, that vast sphere of liquid metal began to churn and swirl, and a spinning core of molten iron does something remarkable. It generates a magnetic field. You cannot see it, you cannot feel it, but it wraps the entire planet in an invisible shield, reaching far out into space. It matters more than almost anything. The sun is not only light and warmth, it also throws out a constant scouring wind of charged particles, radiation that can strip a planet's air away over time, molecule by molecule, until little is left. That is part of what happened to Mars. It had water once. It had air. Rivers ran across it. There may have been lakes, even a shallow sea. But Mars is smaller, and it cooled faster. Its churning interior weakened. Its magnetic shield faded. And once the shield was gone, the solar wind did its slow work, thinning the air across hundreds of millions of years, until the rivers dried, the seas vanished, and Mars became the cold, red, windswept world we see today. A planet that almost made it. A near miss, hanging right next door as a kind of warning. Earth kept its shield. The core stayed hot and kept turning, and kept the field strong enough. And so Earth kept its air and kept its oceans and kept its chance. Two kinds of shelter then formed almost together. One you could touch. the deep, steady water, one you never could, the field that held the whole planet in its arms. Neither was made for life. Life did not exist yet, but the rooms were being readied. The conditions were coming into alignment. The rain still falls in the early oceans. The shield still hums around the planet. And in the warm, mineral-rich dark below the waves, the chemistry's about to get interesting. Let us go down there, into the water, and look closely. Something is beginning to stir. We have to be careful here. This is one of the deepest questions there is, and the honest answer is that we do not fully know. How did life begin? Not life as you picture it. No creatures, no movement, nothing you could see. We mean the very first step. The moment when ordinary chemistry, the kind that happens when the right molecules meet, somehow crossed a line and became something that could copy itself, something that could carry information forward, something that could, in the faintest sense of the word, continue. We have ideas, good ones, but no one was there, and the evidence is almost 4 billion years old. So we will follow what we can, and where the trail goes quiet, we will say so. Picture the floor of the early ocean, not the smooth seabed you might imagine, a fractured, restless place where the planet's inner heat leaks up through cracks in the crust. In certain spots, water seeps down, meets that heat, and comes roaring back up rich with dissolved minerals. Around these openings, towers and chimneys of rock build themselves, dark shapes in the lightless water, with warm mineral-laden currents pouring out of them. We call them hydrothermal vents, and they may be where it all started. Picture one of them, if you can. You cannot see far. The water is black this deep beyond the reach of sunlight. But the vent itself glows faintly with heat, and around it the water shimmers and warps, thick with dissolved minerals. The rock has built strange chimneys, some as tall as buildings, venting dark plumes that look almost like smoke. It is hot, mineral-rich, and utterly without light. A place that sounds like the opposite of where life should begin, and yet it may be exactly where it did. Think about what a place like that offers. A steady source of energy, welling up from inside the planet, not from the sun but from Earth's own heat, reliable, never setting, never failing. A constant supply of raw chemical ingredients, and crucially, structure. The vent rock is full of tiny pores and pockets, countless little chambers where molecules could gather, concentrate and meet one another again and again, sheltered from the open water. In the wide ocean, anything interesting might simply drift apart and dilute to nothing. In those little stone chambers, things could stay together long enough to matter. Warmth, minerals, boundaries, time. If there was a workshop for the first chemistry of life, it may have looked something like this. Maybe it was there, or maybe it was somewhere else entirely. Another possibility is the shallows. Warm pools at the edges of the young land, drying and refilling, drying and refilling. Each time a pool shrank, the molecules inside it were pressed closer together, forced to interact. Lightning split the heavy air and sparked new compounds. Some of the ingredients may even have fallen from the sky, carried in on comets and meteorites, which we know can carry organic molecules, the basic carbon-based building blocks, ready-made. The truth may be that it was all of these, a planet running the same experiment in 1 million places at once for 100 million years, until somewhere, somehow, it worked. And what does worked actually mean? This is the part worth slowing down for. For a very long time, the early ocean was just a soup of molecules drifting and reacting at random. They formed and broke apart, going nowhere. Chemistry without memory. Each reaction forgotten the moment it ended. Lightning split molecules apart and water reassembled them into something slightly new, and then that fell apart too. Compounds gathered in still pools and along shallow coasts grew complex and dissolved again. For millions upon millions of years, the planet ran this experiment with no result that stuck. It was busy. It was rich with chemistry, but it had no way to keep what it made. Then, at some point we cannot pin down, a molecule appeared that could do something new. It could make a copy of itself. That sounds small. It is the hinge the whole story turns on, because the moment something can copy itself, the rules change completely. Copies sometimes come out slightly different. A tiny variation, a small mistake. Most mistakes go nowhere. But every so often, a change makes the molecule a little better at surviving, or a little faster at copying, and those copies make more copies. The change spreads. The next round builds on it. That is the engine. Copying plus small errors plus time. From that simple loop, everything else eventually comes. Every leaf, every wing, every eye, every thought you have ever had. It is, in a sense, the only invention this planet ever truly needed. Everything after is variation. And notice what that means. It means life did not need a goal. There was no plan, no aim, nothing trying to build a human being 4 billion years in advance. There was only this. Things that copied themselves a little better, made more of themselves, and things that did not faded out. That is the whole rule. It can look like striving. It can produce things of staggering beauty and complexity. But underneath it is slow arithmetic, running in the deep, for longer than we can hold in our minds. There is something steadying in that, I think. The grandeur and the simplicity are the same thing, but, and we have to be honest, we do not know exactly how that first self-copying molecule arose. We can build pieces of the path in the laboratory. We can show that certain steps are possible. We can sketch a believable route from plain chemistry to the threshold of life. What we cannot yet do is point to the morning it happened and say, there, that is the one. The crossing itself stays hidden somewhere back in the dark water, almost 4 billion years ago. And it is possible we will never find it, that the first living thing left no trace at all, and that the question will stay open as long as we do. And maybe that is all right. Not every question needs an answer tonight. There is a strange comfort in a mystery this old, one that has waited this long and is in no hurry to be solved. What we can say is this: once it began, it never fully stopped. That thread of copying, of carrying information forward, has run unbroken from that first molecule to the cells in your hands right now. Every living thing you've ever met is a continuation of that faint beginning in the vents or the pools. You're the far end of a line that has not broken once in nearly 4 billion years. Let that sit for a moment. Every direct ancestor in your line, every one of them, across that entire span, survived long enough to pass life forward. Not one link in the chain failed before it could continue. Not through the freezings, not through the extinctions, not even through the asteroid that would later end almost everything. Through all of it, your particular thread held. The same is true of every creature alive tonight, the moth at the window, and the fox in the field, and the person beside you. We are all the unbroken ends of impossibly long lines. It is the most ordinary thing in the world, and one of the strangest. The planet had no eyes yet, no mind, no idea what it had done. The water simply went on, warm and still and full of new chemistry, copying and copying in the silence. Life had started, and the world would never be empty again. Life had started. But it would be a long time before anyone could see it. Not a long time the way we usually mean it. A long time in the scale we have been using. that deep time calendar where a second is 140 years. In those terms, what we're about to cross is most of the year: spring, summer, and a long stretch of autumn. More than 3 billion years in which life existed on this planet and left almost no trace a human eye would recognise. No forests, no animals, no sound except wind moving over water and waves pressing against bare rock. The world was alive. It was just invisible. What life looked like for most of those first ages was almost embarrassingly small. A film. A thin wet coating on submerged stone. Microbial mats. Communities of single-celled organisms pressed close together, sharing what they produced, drifting in a slow chemical conversation with the water around them. They were not plants. They were not animals. They were not really anything we have a comfortable word for. But they were life learning one of its oldest habits. Staying together because staying together worked. The ocean they lived in looked nothing like ours. It was warm, and in places genuinely hot, heated from below by a crust that was still thin and restless. In some stretches the water may have carried a greenish cast from dissolved iron and minerals. Near vents and rifts, sulphur and metal would have given it a chemistry that no swimmer from our world could survive. Above it, the sky was not the clear blue we know. It was hazy, orange-brown, thick with methane and carbon dioxide, lit by a young sun still dimmer than today's, and yet because of that dense greenhouse air the planet stayed warm enough for liquid water. There was no familiar horizon of blue on blue, just a strange sky, a mineral sea and black volcanic rock. No bird song, no insects, no leaves moving in the wind, no ripple made by anything alive above the waterline. In the shallows, where light could still reach through the mineral-rich water, some of these mats built something more permanent. Layer by layer, trapping grains of sediment and binding them in sticky biological films, they raised domed structures of rock, slowly, over centuries. Something like the way coral builds a reef, but slower, quieter, and with nothing like the colour. We call them stromatolites. Some ancient examples come from Western Australia, and forms like them still grow today in shallow coastal waters. They look like rounded stones. They look at first glance like nothing much at all. But they are among the oldest large-scale biological structures on Earth, and for much of this planet's living history, they were the tallest things alive. Stand in front of one if you ever get the chance, and try to feel what you're looking at. Not a single creature unchanged for 3 billion years, of course, but a continuity of biology older than almost everything familiar. A way of living that predates eyes, mouths, bones, roots, and every creaturely thing we usually mean when we say life. The stromatolite does not know you are there. It has never known anything, and yet it belongs to the same long thread we traced earlier, the thread that runs forward through time without a single gap. For much of the Archean eon, the ocean floor was carpeted in microbial life. Bacteria and archaea spread into every available place: rock surfaces, hydrothermal vents, deep sediment, shallow water, perhaps even the underside of ice where ice formed. They moved into worlds with no oxygen, no sunlight, no warmth to speak of. They fed on sulphur, iron, hydrogen, chemical gradients in the water, whatever the Earth happened to offer. They were the world's first explorers, though not because they chose to explore. They simply reproduced until they ran into limits, and then some descendants happened to survive beyond those limits. Life has often worked that way. Not bravery, not intention, just persistence, variation, and space. It is easy to feel impatient during this part of the story. The mind wants a face. It wants motion. It wants something with a body to follow through time. But the microbes were not waiting for the real story to begin. They were inventing metabolism. Not one metabolism either. Many. Fermentation. sulfur reduction, iron-based chemistry, early forms of photosynthesis. Each one was a new way of making a living from the planet, a new agreement between life and the world around it. They did not discover these things by planning. They arrived at them because the variants that worked left more descendants, and over time, working meant something richer. The microbial world was not a single grey smear of life. Different lineages occupied different chemical niches. Some lived near sulfide rising from the seafloor. Some used iron compounds in rock. Some learned to take energy from faint light in shallow water. Some produced waste that became food for others. From a great distance, across hundreds of millions of years, the whole thing begins to look almost like an ecosystem. Not designed, not coordinated, but layered, accumulating, each process fitting into the conditions left by another. A city does something similar in its own human way. No one designs every habit, every shortcut, every market stall, every path people take through it. But given enough time, patterns form. The microbial Earth was not a city. It had no minds. Still, it was already a world of relationships. That matters for the feeling of the story. We tend to imagine relationship as something emotional, something belonging to animals, families, tribes, and later to us. But relationship began much earlier than feeling. It began as chemistry touching chemistry, one organism changing the water, another living from what that change made possible. Long before affection, long before fear, long before recognition, life was already entangled. We are the beneficiaries of that invisible work. The way your cells break down food, produce energy, repair themselves, regulate heat, the deep chemistry that keeps you alive tonight, has roots in that long microbial laboratory. The microbes did not build it for us. They built it for themselves, in a world that had no idea we were coming. We inherited it the way you inherit a house built long before you were born, by people who would never have recognized your name. The record from this era is thin and difficult. Soft bodies leave faint impressions. Single cells leave almost none. What we have are chemical traces in rock, rare microfossils, stromatolites, and the stubborn signatures of life changing the chemistry around it. The Archean is one of those chapters we can only read in outline. The gaps are not small, they are the size of oceans. There is something disorienting about that. For 3 billion years the world was genuinely, richly, busily alive, and yet if you had stood on the shore of the early ocean, you would have seen almost nothing. Water, rock, wind moving the surface, maybe the low dome shapes of microbial mats at the waterline if you knew to look. No movement on land, no flight, no colour that was not mineral. A world dense with chemistry, legible to no one, observed by no one, heading nowhere in particular, and still building the foundation for everything that would follow. By the time we reached 2.5 billion years ago, the ocean was full in ways we can barely reconstruct. A richness that took most of a world's history to accumulate. None of it visible from more than a few millimeters away. None of it making a sound. The microbes were not the prelude. They were the longest chapter this planet ever wrote, and one of them was about to exhale a new world into being. Of all the things the invisible Earth produced, one small invention remade the planet more thoroughly than almost anything before it. It began with cyanobacteria. Cyanobacteria were not the first organisms to use sunlight. Earlier microbes had already learned versions of photosynthesis, pulling hydrogen from sulfur compounds or other sources to power their chemistry. But by around 2.5 billion years ago, perhaps earlier, the dating is still being refined, cyanobacteria crossed into something new. They learned to split water. It sounds technical. It is also one of the reasons you are alive. When a cell splits water, It takes the hydrogen it can use and releases oxygen it cannot. Oxygen at first was not a gift to the future. It was waste, a leftover. The cyanobacterium released it the way we release carbon dioxide when we exhale, simply because it was what remained after the useful part had been taken. Life was exhaling oxygen long before oxygen was breathable. At first, that oxygen went almost nowhere. The oceans were full of dissolved iron, and iron reacts eagerly with oxygen. It rusts. On the early Earth, it rusted on a planetary scale. For millions of years, oxygen produced by cyanobacteria combined with iron and settled onto the seafloor as banded iron formations. Dark and red stripes of mineral in rock, laid down layer after layer by an ocean slowly changing its chemistry. If you've ever seen iron ore or steel or the red dust of rust on an old piece of metal, you've seen a distant echo of this process. Much of the iron ore humans later mined for ships, railways, bridges, towers, weapons, tools, and machines came from those ancient ocean floors. The infrastructure of modern civilization rests in part on the rust of seas older than animals. That connection is rarely visible, but it is there. For a long time, the ocean absorbed the oxygen as fast as life produced it. Chemistry ran in the only direction available. Iron took the oxygen. The seafloor kept the record. The air above changed only slowly, if at all. But eventually the sinks began to fill. The dissolved iron ran low. The ocean's capacity to hide the oxygen weakened, and the gas had nowhere to go but up. It entered the atmosphere slowly, over millions of years. The sky began to shift. Methane, which had helped keep the young Earth warm under its dimmer sun, reacted with the new oxygen and broke down. The old orange-brown haze thinned. The air became chemically different from anything Earth had known before. High above, another change began. Oxygen molecules struck by ultraviolet radiation recombined into ozone. A thin, diffuse layer started to form, absorbing some of the very radiation that had created it. Before ozone, the surface of the Earth was exposed to ultraviolet light intense enough to damage the fragile chemistry of life. Water had been the only real protection. Life stayed below the surface because the open land was not yet a place life could safely be. Now, very slowly, that lock began to turn. Not enough for forests, not enough for animals, not for hundreds of millions of years. But the first part of the future land world was being made in the sky by organisms that never left the water. This is one of the strange patterns that keeps returning in Earth history. A change begins in one place, for one reason, and its meaning only appears somewhere else, much later. Oxygen began as waste in shallow seas. Hundreds of millions of years afterward, it would become a shield above the land. Much later still, it would become breath in lungs, flame in hearths, and energy in human muscle. For much of the life already here, though, oxygen was not possibility. It was disaster. The anaerobic microbes that had built the living world had evolved in the complete absence of oxygen. Their chemistry was not prepared for it. Oxygen reacts, it oxidizes. To a cell shaped by an oxygen-free planet, it is not air, it is acid. This is what we call the Great Oxygenation Event, and it may have been the first mass extinction in Earth's history. Not an asteroid, not a volcano, life itself, exhaling. Sit with that for a moment. The same process that made our atmosphere began as a crisis for the organisms that were alive at the time. The cyanobacteria were not villains. They were not saviours. They were not trying to do anything beyond living. But living in this case changed the rules for everyone else. Some anaerobic life retreated into places oxygen could not easily reach. Deep mud, airless sediments, cracks in rock, stagnant water, the guts of later animals. Their descendants are still there. living by metabolisms that belong to that older world. They do not need the air we need. In fact, many of them would find it lethal. Our breath is their poison, the way theirs would be ours. Other lineages adapted. Slowly, through variation and time, some organisms learned first to tolerate oxygen, then to handle it, and finally to use it. Because oxygen, dangerous as it is, carries power. A cell that can harness oxygen can extract far more energy from the same food than life could before. Not a little more, a different scale of return. That extra energy mattered. It made larger cells more possible. It made more complex internal machinery easier to support. It gave life room, eventually, to become more elaborate than it had ever been. Every breath you take is the inheritance of that adaptation. The oxygen moving through your lungs right now was not placed there for you. It was released first by microbes that had no idea what they were making possible, into a world that mostly could not survive it. And the fact that your cells can run on it, that it powers the movement of your eyes, the warmth of your hands, the private weather of your thoughts, is the result of life learning across unimaginable time to turn catastrophe into fuel. The air was made before us, by organisms that never knew us, for reasons that had nothing to do with us. And yet here we are, breathing it. Oxygen reshaped life. It also reached into the climate. The first consequences came early. Methane is a powerful greenhouse gas, and for much of the young Earth's history, it helped keep the planet warm under a sun that was still dimmer than today's. As oxygen rose, it reacted with methane and stripped some of that warmth away. The planet began to cool. Around 2.5 billion years ago, during a period often linked with the Huronian glaciations, ice advanced across parts of the world on a scale Earth may never have seen before. But Earth returned to deep cold more than once. The most famous and severe Snowball Earth episodes came much later, roughly 700 to 600 million years ago during the Cryogenian. By then, life had been running for more than 3 billion years. The continents had moved, the atmosphere had changed, the biosphere was more complex than it had been during the first oxygen crisis, and somehow, through a mixture of geography, chemistry, sunlight, carbon and ice, the planet came close to locking itself inside a frozen shell. Perhaps it did. The mechanism is easy to describe and hard to really feel. Ice reflects sunlight, so when ice spreads, the planet absorbs less heat. With less heat, more ice forms. More ice reflects still more sunlight. Once that loop passes a certain threshold, it begins to feed itself. The glaciers move toward the equator. Oceans sealed over. The land disappeared beneath white. Imagine standing at the equator, the warm belt of our world, and finding only a frozen plain. The ice perhaps kilometers thick. The sky hard and pale. The air dry enough to hurt your lungs. The ocean present but locked below your feet. Rock buried. Coastlines erased. Wind moving across a white surface with no trees to stop it, no soil to hold it, no animal large enough to leave a track. It may be the loneliest landscape Earth ever wore. There is no good human comparison for that kind of cold. Winter, to us, is seasonal. Even the harshest glacial landscapes we know exist, under a sky that still belongs to a living world, with microbes in the soil, birds at the edge, distant forests somewhere beyond the ice. Snowball Earth was not a winter. It was closer to a planetary pause, not absolute, not dead, but held so tightly that almost all visible change disappeared. The planet was not dead. That matters. Life had been running for too long, in too many places to vanish all at once. Under the ice, where geothermal heat kept water liquid, microbial communities continued. Around hydrothermal vents on the seafloor, life carried on almost indifferent to the frozen sky above. Inside thin films of liquid water trapped within ice, some organisms may have persisted in narrow chemical worlds we are still learning how to understand. Near volcanic regions, patches of open water may have remained. If they did, they would have been refuges. Not safe, exactly, but enough. Life survives before it understands survival. There was no recognition of crisis. No organism knew it was enduring an age. There was no strategy called resilience. There were only traits meeting conditions. Some forms of life had the right chemistry. Some occupied the right place. Some were simply carried by chance into the few environments that still allowed metabolism to continue. Survival, at this scale, is fit, place, and luck braided together so tightly that you cannot always tell them apart. Through all of it, volcanoes kept working. Deep beneath the ice, the Earth's interior continued to release carbon dioxide through vents and rifts. Normally, exposed rock and open oceans help draw that carbon dioxide back down. But on a frozen Earth, rock was buried and the ocean was sealed. The gas accumulated, not quickly. Nothing here is quick. Molecule by molecule, eruption by eruption, across millions of years, carbon dioxide rebuilt a greenhouse above the ice. It is less potent than methane, but it persists. It waits in the air and gathers strength by accumulation. Eventually the arithmetic tipped. The thaw probably began almost invisibly. A slight warming at lower latitudes, a patch of darker surface exposed, a little more sunlight absorbed, then more exposed water or rock, which absorbed still more heat. The feedback reversed. What had once pushed the planet into ice now helped pull it out. By geological standards, the melt may have been fast. Thousands of years, perhaps, though that is still a span larger than all recorded human history. Ice retreated. Oceans opened. The atmosphere, loaded with carbon dioxide, may have turned the world from frozen stillness into a hot, stormy greenhouse. Rivers and meltwater poured across newly exposed rock, and the meltwater carried a gift. Glaciers are not clean. Over millions of years they grind rock to powder and trap the mineral remains inside themselves. Phosphorus, iron, nitrogen compounds, a whole vocabulary of continental chemistry. When the ice finally melted, those nutrients poured into oceans that had been starved and sealed for ages. The response was not instant, but it was profound. Microbial communities expanded into newly enriched water. Metabolisms found fresh opportunities. Eukaryotic organisms, the more complex cells waiting beneath this story, had already been evolving quietly for hundreds of millions of years. In the aftermath of Snowball Earth, they may have found something they had not had before: open water, nutrients, disturbance, oxygen, and space. In ecology, upheaval creates openings. What grows into them depends on who is left, where they are, and what they can do. We do not know exactly how many Snowball episodes there were, or how complete the freezing was each time. Some researchers argue the ice reached the equator. Others think open water survived near the tropics, keeping more of the biological world exposed to light than a true snowball would allow. The rocks from this period are difficult and contested. They do not give up their story easily. What we can say is enough. Something survived, and what survived was ready in time to become stranger. Before we follow the ocean into the next visible world, we need to step sideways in time. The complex cell did not appear only after Snowball Earth. Its machinery had been assembling much earlier, perhaps around 2 billion years ago, perhaps closer to 1.5. The dates are not fixed in stone the way we might like them to be. The record is patchy, and new evidence keeps moving the edges. But by the time the great cryogenian ice came and went, eukaryotic life, the kind of cellular life that would eventually produce animals, plants, fungi, and us, had already been preparing itself for a very long time. So what made these cells different? For most of Earth's living history, life had been prokaryotic, cells without a true nucleus, without the internal compartments found in our cells. Prokaryotes are not failed attempts at complexity. They're astonishingly successful. They are small, fast, flexible, and capable of surviving conditions that would kill nearly everything else. They still dominate Earth by number. In many ways, this is still their planet. But there are limits to what can happen in one open room. At some point, cells appeared with internal membranes, with a nucleus where genetic material could be stored and managed separately from the rest of the cell's busy chemistry, with compartments that allowed different reactions to happen in different places. A cell was no longer only a bag of living chemistry. It had rooms. It had boundaries inside itself. We call these cells eukaryotes. We are made of them. Their origin is one of biology's great stories, because it is not simply a story of one lineage becoming more elaborate on its own. It is a story of merger. The leading explanation, supported by genetic and cellular evidence, is that an ancient host cell, probably from the domain we now call archaea, engulfed a bacterium and did not digest it. Maybe it failed to. Maybe the relationship was parasitic at first. Maybe it was already useful. We do not know the first moment, but somehow the smaller cell survived inside the larger one, and then the relationship held. The bacterium supplied energy. The host supplied protection, resources, and a stable internal world. Generation after generation, the boundaries blurred. The bacterium lost genes and structures it no longer needed. The host became dependent on the energy it provided. Eventually, the guest was no longer a guest. It was part of the cell. We call its descendants mitochondria. You have them in nearly every cell in your body. They are working right now, quietly producing the energy that lets you read, blink, breathe, remember, and stay warm. Here is the detail that still feels strange no matter how many times it is explained. Your mitochondria have their own DNA, a small separate genome, distinct from the DNA in your cell's nucleus. It is the residue of that ancient merger, the molecular trace of a partnership older than all animals, older than plants, older than anything that ever walked or watched the sky. When you breathe in and your cells use oxygen to generate energy, that work happens inside your mitochondria. They are performing a version of a bacterial metabolism that began long before there was anything with a face. That is not a metaphor. It is biochemistry. Plant cells carry another version of this old intimacy. Their chloroplasts appear to descend from cyanobacteria, the oxygen-producing lineage we followed earlier when oxygen first entered the story. If so, then the organisms that once released oxygen as waste, destabilizing the world they lived in, are also ancestors of the structures inside leaves that capture sunlight today. The catastrophe became an engine. The waste became a way for life to harvest light. Eukaryotic cells, larger and more internally organized, powered by resident partners, could do things prokaryotes generally could not. They could carry more genetic material and regulate it more carefully. They could grow larger. They could build internal structures for particular jobs, and eventually some of them began to live in groups that did not simply break apart after division. At first, a cluster, then a more stable cluster, then, in some lineages, division of labour. One cell doing one kind of work, another doing something else, some cells helping the body move, some helping it feed, some helping it reproduce. Multicellularity almost certainly arose more than once in different branches of life. Algae found one path, fungi another, animals another still. The details differed, but the underlying idea was the same. A body can do what a single cell cannot. This is easy to say and hard to feel. A body is not just more cells, it is an agreement among cells, enforced by chemistry, inheritance, and need. Some cells give structure, some move, some sense, some digest, some defend. None of them, alone, is the animal. The animal is the arrangement. Long before humans had families, villages, language, or fire, life had already found that survival could mean joining together. The whole can do things the parts cannot, and sometimes giving something up. Specialization always means surrendering some freedom, becomes the beginning of a new kind of strength. There was no plan in this. Single-celled life was not trying to become animals. Cyanobacteria were not trying to prepare the air. The first eukaryotes were not waiting for eyes, hands, forests, or human thought. Certain arrangements simply worked under certain conditions, and life kept what worked. That is all. It is simple enough to sound almost disappointing. Given enough time, it produces outcomes that look like intention. Multicellularity also introduced a quieter consequence. Once cells specialize, not every cell carries the future forward. Some reproduce, many do not. A body, in the biological sense, is built largely from cells that will die with it, supporting the smaller number that pass the line onward. Here, faintly, is the beginning of a distinction that will matter to every animal that ever lives. The lineage continues, but the individual ends. Sexual reproduction added another layer. Instead of copying and slightly varying, two organisms could combine genetic material, producing offspring that carried something of both. Variation became richer, faster, more flexible, and variation is the raw material survival uses when the world changes. By around 600 million years ago, the basic toolkit of complex life was in place. Nuclei, mitochondria, in some lineages chloroplasts, the capacity for multicellularity, sexual reproduction. Larger bodies were not inevitable, but they were now possible in a way they had not been before. The ocean was still ruled in sheer number by microbes. It still is. But in the shallow waters after the great ice ages, something had been gathering for a long time. Cells with more energy, more internal structure, more ways of cooperating, more ways of varying, more ways of becoming. Not yet animals, not yet anything with a face or a body you would recognize. But the groundwork was laid. The machinery was ready. The energy was available. The world was about to get complicated. Eyes were coming. And with them, the possibility that life would not only exist in the world, but begin in small flashes to notice it. For 3.5 billion years, the ocean had been full of life that could not see, not fully dark. Light reached the shallows. It fell through the surface in pale, shifting columns, touched the sediment, glanced off microbial mats, dissolved into greenish water. But no eye gathered that light and made an image from it. Nothing looked back. Whatever happened in those early waters happened unseen, even by the organisms doing it. Then, somewhere around 540 million years ago, and across the tens of millions of years that followed, something changed. Not overnight, not in one place, not as cleanly as the word explosion makes it sound. But in geological terms, quickly enough to feel almost sudden. Body plans appeared, hard parts, appendages, mouths, nerves, eyes. We call it the Cambrian explosion. The name carries drama, and in this case the drama is not entirely wrong, but it can mislead. Animals did not appear from nowhere one morning in a finished world. The Cambrian built on everything that came before it. The oxygen, the complex cells, the long experiments in multicellularity, the strange soft-bodied organisms of the Ediacaran seas. Those Ediacaran organisms, living roughly between 635 and 540 million years ago, already made the ocean look different. Some were disc-shaped and fixed to the seafloor. Some were quilted, ribbed, or fern-like, as if life had tried out patterns it would later mostly abandon. Dickinsonia, one of the most famous, grew as a flat ribbed oval, sometimes close to a metre across. Most evidence now points toward it being an early animal, though its exact place in the tree of life still carries uncertainty. What matters here is that these were large, multicellular beings. They were real presences in the world. But they had no hard shells, no obvious jaws, no eyes as we would understand them. They left very little evidence of behaviour. They were there, pressed into the ancient mud. Then, by the Cambrian, many of them were gone. Whether they were eaten, outcompeted, or simply overtaken by a new kind of ecology is still not fully clear. In the fossil record, they can feel like a first draft the world quietly set aside. The Cambrian is when the rock begins to remember more. Shells hardened, skeletons formed, animals burrowed and left trails, bodies gained structures durable enough to survive burial, pressure, and 500 million years of waiting. Picture an early Cambrian seafloor, not the nearly still surface of the Archean, carpeted in microbial mat, but something layered and restless. Worms move through sediment, leaving tunnels behind them. Sponges filter water from fixed positions. Flat-bodied creatures glide just above the bottom. Tiny animals test the mud, the water column, the edges of reefs, and among them are the first animals with something close to eyes. Photoreceptors arranged not merely to detect light, but to find direction, shape, shadow. That changes the world. Before eyes, the difference between light and dark mattered chemically. With eyes, it began to matter behaviourally. A shadow could mean danger. Movement could mean food. Distance could be judged. The world was no longer only touched, tasted, or chemically sensed. It could appear. Trilobites were among the earliest and most successful sighted animals. They looked a little like large segmented woodlice, though that comparison makes them sound more ordinary than they were. Some were smaller than a fingernail. Others grew much larger. Their bodies were armoured in calcite, and many carried compound eyes so sophisticated that their geometry still impresses people who study optics today. They survived for nearly 300 million years and left fossils by the millions. There is something strange about holding one. A trilobite is not merely an old shell. It is the trace of a creature that moved through a world of light and shadow, long before there were forests, flowers, birds, or mammals. You can see where its eyes were. You can see the arrangement of lenses in stone. It is one of the oldest gazes we can still study, looking back through geological time without ever having known it was looking at all. Anomalocaris was different, a predator perhaps approaching a metre in length, with stalked eyes, grasping appendages, and a circular mouth built for holding and tearing. It was among the largest animals of its time, and it was hunting. That word is new to this story. For billions of years, life had encountered resources or failed to. It had spread, divided, metabolized, endured. Now something was pursuing something else. Predation does not only change the predator, it rearranges the whole room. If one animal can chase, another must hide. If one can bite, another grows armour. If one can detect movement, another learns stillness, camouflage, or speed. The ocean becomes a place of appearances and concealment, of attention paid and attention avoided. The body becomes a problem to solve. How to move, how to sense, how to protect what can now be found. Nervous systems were part of that change. They didn't appear complete. Nothing does. They built up over time, from simple nets of nerves to more centralized forms of coordination. But by the Cambrian, some animals were already integrating signals from multiple senses and producing organized movement in response. This is the distant ancestry of perception, of reaction, of something like fear, though we should be careful with that word. Still, you know a small version of this ancient inheritance. When something moves suddenly at the edge of your vision and your body reacts before you understand why, that response comes from circuitry much older than conscious thought. You share versions of it with fish, frogs, lizards, birds. Its deepest ancestry belongs to a world where a quick response to motion could mean the difference between continuing and ending. The ocean was where nervous systems first learned to answer before they could think. Early chordates also appear in Cambrian deposits, animals with a dorsal nerve cord, part of the lineage that would eventually lead to vertebrates. Some of the most famous fossils come from the Burgess Shale in what is now the Canadian Rockies. There, roughly 508 million years ago, a submarine mudslide buried animals so quickly that even soft tissues were preserved. The result is one of the rare places where the fossil record lets us see bodies, not just hard parts. Flattened, dark, delicate traces of organs, muscles, outlines. Pangaea, a small eel-like animal found there, is among the earliest possible chordates we have identified. It was not imposing. It was soft, narrow, easy to overlook beside stranger Cambrian animals with claws and armour. But the line it belonged to would eventually produce fish, amphibians, reptiles, mammals, and a species that would climb into those mountains, split open that shale, and find a faint ancestral shape waiting in the stone. Reef builders constructed early carbonate structures, algae diversified, mollusks appeared, worms churned the sediment. The ocean, once organised mostly around chemistry and proximity, reorganised itself around behaviour, sensing, moving, pursuing, evading. The moment life opened its eyes, the world became a place of appearances. It is tempting from where we stand to make that sound beautiful. Eventually it would be. Eyes would look at mates, offspring, stars, firelight, painted walls, the faces of the dead. But at the beginning, vision was probably much simpler and much harsher. It made danger visible. It made distance useful. It turned the world into something that could be searched, escaped, and misread. Beauty would come later. First came shadow, not only in the literal sense. Something was added to existence, the possibility of being seen, of mattering to another organism not as a chemical gradient but as a shape, a shadow, a moving presence in space. The world had always been full of processes. Now it began to fill with encounters. That distinction is easy to miss because we live inside it so completely. Recognition, attention, alarm, curiosity, connection. These feel like human experiences. But their roots are much older than humanity, older than mammals, older than land animals. Somewhere in a Cambrian sea, light became image, image became behaviour, and the ocean was never the same again. The ocean was crowded now. After the Cambrian reorganisation, life had bodies, senses, movement, behaviour. By the Ordovician and Silurian periods, roughly 450 to 400 million years ago, the seas were rich and layered. Reef systems, armoured fish, mollusks, arthropods, worms, sponges, and all the hidden labour of microbes still beneath them. Above the waterline, almost nothing. The rocks were bare, wind-scoured, sun-blasted. No roots held the surface together because there was no real soil yet. Only mineral particles, weathered stone, and in the dampest places perhaps a thin crust of algae and bacteria. The land was not empty in the old Archean sense. It was not lifeless. It was empty the way a room is empty when you can hear people just outside the door. Life was already pressing against the threshold. The first organisms to take that threshold seriously were not animals. They were the lineages that would become plants, beginning from green algae in shallow coastal water. Over vast stretches of time, some of them developed traits that allowed longer exposure to air, waxy coatings to slow water loss, simple conducting tissues to move water through a small body, spores that could survive drying out. None of this was planned. No plant was trying to leave the sea. There was only variation, generation after generation, at the edge where water met air. Some forms dried too quickly. Some endured a little longer. Those that endured left more descendants. The shoreline kept asking the same question, and life kept answering imperfectly. There must have been countless failures we will never see. Mats that dried out before they reproduced, spores that did not survive the sun, green fringes along tidal flats that advanced for a while and then vanished when climate shifted or salt changed, or a storm tore the surface clean. Evolution remembers the successful lines because they are the ones that leave descendants. The failures disappear almost completely, but they were part of the experiment too. By around 450 million years ago, something we can honestly call plants existed on land. Small, rootless, or nearly rootless, low to the ground but genuinely terrestrial, able to photosynthesize in open air, reproduce there, and hold their place against the drying wind. They were not trees, not even close, no leaves, no flowers, no branching complexity, more like green films, ribbons or tiny spikes clinging to damp rock near the water's edge. But they were there, and once life is there, it begins to change the place it occupies. Fungi may have been essential partners in that transition. The relationship between plants and certain fungi, called mycorrhizae, is one of the most widespread partnerships in terrestrial life. Fungal threads extend through soil far beyond the reach of roots, gathering phosphorus and other minerals for the plant, while the plant provides sugars made from sunlight. In early land plants, with root systems barely developed, that fungal partner may have been the difference between surviving and failing. Some of the oldest plant fossils already show signs of this association. It is a quiet thing to imagine. Life arriving on land not as an individual hero, but as an alliance. Plant and fungus intertwined from the beginning, negotiating with stone. The forests we walk through still rest on versions of that old agreement. As plants established themselves, the rock beneath them changed. Roots, even primitive ones, do not simply anchor a body. They break rock apart. They release weak acids. They open minerals, they dye and add organic matter to the accumulating particles below. Bacteria and fungi continue the work, breaking dead material into simpler compounds that cycle back through the system. Slowly, across millions of years, the first soils formed: broken rock, dead life, fungal threads, microbial communities, water, air, chemistry. Soil is not simple geology. It is biology made durable. It is the land's memory of everything that has lived in it. With soil came stability. With stability came more plants, and with more plants came more soil. The feedback gathered slowly at first, then with increasing force. The land, which had once been a surface, began to become a habitat. Animals followed. Arthropods, the lineage that includes insects, spiders, millipedes and crustaceans, were already partly prepared for the experiment. Their exoskeletons helped resist drying. Their jointed legs could support weight against gravity. Their breathing systems, with openings that admitted air to internal tubes, offered a workable way to live without gills. The first terrestrial arthropods appear in the fossil record around 430 million years ago. Millipede-like creatures moving through new soil, feeding on decaying plant matter, sheltering in dampness near the surface. They were not pioneers in the heroic sense. They did not bravely set out to colonize anything. Their bodies simply worked well enough in a new place. That is how most thresholds are crossed in evolution, not by ambition, but by accident made repeatable. Back in the water, another transition was beginning. Lobe-finned fish with muscular fins supported by bones arranged in ways that prefigure the bones in your own arm, were becoming significant in shallow, swampy, oxygen-poor environments. When the water held little oxygen, some could supplement gill breathing with air breathing. When pools dried or grew stagnant, some could drag themselves short distances through mud to reach better water. Again, nothing here was aiming at land. These were animals solving immediate problems in difficult shallows. But over millions of years, fins became something closer to limbs. The fossil record gives us a remarkable glimpse of the transition in Tiktaalik, discovered in the Canadian Arctic in 2004. Tiktaalik lived around 375 million years ago. It was fish-like, but not simply a fish. It had a flat head, a neck it could turn, and fins containing bones that resemble an upper arm, forearm, and something approaching a wrist. It could probably prop itself up. It could lift its head toward the air in a way earlier fish could not. What it was doing with those proto-limbs is still debated. Bracing against the bottom of shallow water, perhaps, lifting itself in muddy margins, moving awkwardly between pools. It was almost certainly not trying to reach land in the way we imagine. But its body had the architecture. The bones were there. The joints were there. Given enough time in shallow, unstable environments, those structures could become limbs that bore weight. The first true tetrapods, four-limbed vertebrates with recognizable wrists, ankles, and digits, appear around 370 to 360 million years ago. They were still deeply tied to water. They fed in it, bred in it, returned to it. On land, they were probably slow, vulnerable, and clumsy compared with arthropods that had already been there for tens of millions of years. But a new body plan had reached the shore. A spine, a head, limbs, lungs, eyes, and a nervous system that could map the world above the water. Every human footstep on land begins here, at the edge of a Devonian pool, with animals that had not quite left the sea. The shoreline was not a destination. It was an experiment, repeated over millions of years, with most attempts failing and a few succeeding just enough. Life did not conquer land the way an army takes a city. It crept in from the margins. It dried out, retreated, returned, changed. The air was harsh. Gravity was expensive. Exposure was dangerous. But the space was there. Plants to eat, soil to hide in, sunlight falling on open ground. The shoreline, for all its difficulty, was an opening. By the Devonian period, roughly 400 to 360 million years ago, land plants were no longer only films and low growth at the margins. Trees had appeared. The word tree can sound ordinary now. It should not. For most of the planet's living history, the tallest biological structures were mats and domes in shallow water, stromatolites rising slowly from the seafloor. Now the land itself held vertical life. Trunks lifted canopies into the air, roots deepened the ground, shadows gathered beneath living columns of wood. In the Devonian and then the Carboniferous, forests spread. Progymnosperms, lycopsids, tree ferns, horsetails, names that feel technical, but what they made was simple to understand. The first true woods, the first deep shade on Earth. That phrase is easy to pass over, but it matters. Shade is a kind of habitat. Under a canopy, moisture lingers, temperatures soften, small animals can hide. Dead matter accumulates instead of being stripped away immediately by sun and wind. A forest does not simply occupy land. It changes the terms of being on land. It makes rooms, corridors, shelters, edges. It gives life places to wait. Stand in one of those forests for a moment, as far as imagination allows. The air is warm and heavy with moisture. The light arrives filtered and green. The ground is soft, spongy with plant matter that has not fully decayed. There are no birds in the canopy, no mammals moving through the undergrowth, no flowers, no fruit as we know it. The sounds are few: wind through fronds, insects or arthropods moving low in the damp, the occasional crash of a dead trunk falling into the swamp. The forest is alive, but it has not yet learned to sound like a modern forest. Roots pushed into soil and deepened it further. They reached into rock, released acids, drew minerals upward, died, and added their bodies to the ground. Fallen leaves and branches decomposed slowly. In fact, for a long stretch of the Carboniferous, they decomposed so slowly that whole landscapes began to accumulate dead wood faster than they could break it down. One reason was lignin, the tough structural compound that gives wood much of its strength. The organisms capable of efficiently breaking it down had not yet fully developed the enzymatic toolkit that later fungi would use, so the wood piled up. It sank into waterlogged swamps. It was buried under more growth, more mud, more time. In the warm lowlands of what are now North America and Europe, enormous quantities of plant matter accumulated in places where oxygen was low and decay was incomplete. Buried, compressed, heated, and pressed across millions of years, that plant matter became coal. Long before humans learned to make machines, the fuel for those machines was growing as trees in a swamp. The Carboniferous atmosphere carried more oxygen than ours does today, perhaps 30% or more, compared with about 21% now. That abundance changed the scale of some animals. Giant arthropods appeared, millipedes over 2 meters long, dragonfly-like insects with wingspans wider than a crow's. Arthropods breathe through networks of tubes that carry air directly into their tissues, so the concentration of oxygen places limits on how large they can become. In Carboniferous air, those limits stretched. Fire also behaved differently. With oxygen so high, flames ignited more easily and burned more fiercely. Fossil charcoal, called fusain, appears in Carboniferous rocks, in quantities suggesting wildfire was a regular part of those forests. The first forests were also some of the first ecosystems repeatedly shaped by burning. Fire was not a human invention. It was already part of the planet's grammar, written into landscapes long before any creature could carry an ember deliberately. The forests themselves were unlike anything alive now. Lepidodendron trees, leucopsids with bark marked by diamond-shaped leaf scars, grew 30 meters or more and died relatively young. They toppled into swamp water and sank. Layer after layer accumulated. Each coal seam in the rock record is a vanished forest compressed into darkness. Ancient sunlight, stored in leaves, buried, waiting. There is a stillness to this image that is hard to shake. The coal that later powered the Industrial Revolution, the engines, the ironworks, the railways, the heated cities, the factories, the lights, was sunlight. Not metaphorically. Photons from the Carboniferous sun struck leaves, were captured by photosynthesis, stored in carbon bonds and hidden underground for 300 million years. When humans burned coal, we released that old light. We opened those bonds and returned hundreds of millions of years of stored carbon to the air in the span of a few human generations. The sky responded as it always has to what was placed inside it. The Carboniferous forests locked away enough carbon to help change the climate. Oxygen rose, carbon dioxide fell, ice grew near the poles. Then, as the continents continued assembling into a supercontinent, the warm inland swamps that had sustained those forests began to dry. The great coal forests retreated, the peat remained. The carbon stayed underground in the dark. Life had left itself a long, slow fuse. The continents had been moving all along. They always are. Drifting, colliding, splitting, grinding against one another so slowly that a human lifetime notices almost nothing, while geological time sees entire worlds rearranged. By roughly 300 million years ago, most of the land had gathered into one mass, Pangaea, a single supercontinent stretching across latitudes, surrounded by the vast ocean Panthalassa, with the Tethys Sea cutting into its eastern side. It was a dramatic arrangement, but not a gentle one. The interior lay far from any moderating ocean. Deserts spread across enormous regions. Seasons became extreme. Fierce heat, hard cold, long dryness, storms that could not reach far enough inland. The coasts were more hospitable. The centre was severe. Life adapted as it always had. Reptiles were particularly suited to this new world. Their scaly skin resisted water loss. Their bodies handled dry interiors better than amphibian bodies could. Most importantly, they carried the amniotic egg, one of the great inventions of life on land. The amniotic egg is, in its way, a portable ocean. Inside its membranes, the embryo develops in fluid, protected from drying out, no longer dependent on being laid directly in water. This did not erase the ancient sea from vertebrate life. It sealed a version of it inside the egg. A reptile carrying water in every generation could go where the land went. Synapsids, the reptile-like lineage that would eventually give rise to mammals, diversified across Pangaea. Dimetrodon stalked river margins with its sail-like back. Dicynodonts, stocky and tusked, grazed across drier regions. In the seas, ammonites spiraled through open water, reefs hosted dense communities, and fish continued exploring forms we would almost recognize. The Permian period, from roughly 300 to 252 million years ago, was not a waiting room before disaster. It was a flourishing world. Life had survived the drying of the coal swamps, the assembly of Pangaea, the harsh interiors, the shifting climates. It had filled them as best it could. Then the ground beneath what would one day be Siberia began to open. Around 252 million years ago, the crust split across an immense volcanic province. Lava did not simply erupt from one mountain. It poured from fissures across a region so vast that describing it almost makes it sound imaginary. Layer upon layer of flood basalt spread over what is now northern Russia, in places kilometers thick. The eruptions may have continued in pulses for hundreds of thousands of years or longer. The lava was destructive. The gases were worse. Carbon dioxide poured into the atmosphere and drove warming faster than ecosystems could adjust. Sulfur compounds contributed to acid rain. Rivers and soils changed chemistry. Warming oceans may have released methane from sediments, compounding the greenhouse effect. As the oceans warmed and circulation weakened, large portions of the seafloor lost oxygen. Anoxic zones spread. Hydrogen sulfide, toxic to most complex life, may have risen from the depths into surface waters, perhaps even into the air near coastlines. The world was being poisoned from below. It echoes strangely the oxygen crisis 2 billion years earlier, when microbes transformed the planet by releasing a reactive gas. But the rhythm was different now. The visible world was full of animals, forests, reefs, bodies that needed oxygen and stable chemistry. They did not have millions of years to adjust. This time, the change came in thousands. For human life, 1,000 years is almost beyond feeling. For the Earth, it is a shock. Forests cannot migrate fast enough. Reefs cannot rebuild while the water around them turns hostile. Food webs that depend on timing, temperature, oxygen, and chemistry begin to tear at the seams. One species disappears, and the things that fed on it or sheltered in it or lived beside it are exposed. Collapse is rarely a single blow. More often, it is a series of supports failing faster than life can replace them. What followed is the Permian-Triassic extinction, often called the Great Dying. Roughly 252 million years ago, in geological terms almost instantaneously, ecosystems collapsed. Perhaps 70 to 90% of marine species disappeared. On land, many vertebrate lineages vanished as well. Numbers this large can create a false sense of precision, so it is better to say it plainly. Most life in the ocean died. Much of the complex life on land was broken apart. Reef systems that had been building since the Cambrian vanished. Ammonites nearly disappeared. Trilobites, those armoured animals with compound eyes, survivors of nearly 300 million years of extinction, predation, and continental rearrangement, ended here. Finally and completely. After everything else they had outlasted. Sit with that for a moment. Trilobites had been on Earth since before forests, before tetrapods, before reptiles, before Pangaea. They had survived changes so large that whole worlds came and went around them. The Permian-Triassic event ended them. No form of life is promised continuation. Something survived. It always has, but never easily. The lineages that passed through the Great Dying were few, and many were small, and some had simply been in places buffered from the worst of the heat, acid or oxygen loss. Higher ground, deeper burrows, more stable pockets of water, narrow refuges. From these remnants, over millions of years, life would rebuild. But recovery was slow. Some estimates suggest that fully complex marine ecosystems took 10 million years or more to return. The early Triassic was a sparse world compared with what came before, simplified, strained, dominated by survivors rather than abundance. The old cast was gone. The stage had not been cleared in any clean or purposeful way. It had been damaged, emptied, and left to whatever could still live there. And still, the survivors mattered. Reptile lineages would diversify in directions no Permian ecosystem had contained. Small synapsids, ancestors of mammals, would continue in the margins. The volcanoes eventually quieted. Carbon dioxide began its slow return toward balance. The air cleared little by little. The seas recovered, not by restoring what had been lost, but by building something else from what remained. The world after the Great Dying was not the world before it. It never is after a loss like that. For now, let the silence hold. The Permian is over. The Triassic morning is cold and thin, full of survivors who do not yet know what they have inherited. The Triassic morning was sparse, not empty. Life had made sure of that. But sparse in the way a place feels after something has passed through and taken most of its depth with it. The Permian extinction had not erased the living world. It had thinned it. Food webs that once had many layers were reduced to a few surviving threads. Oceans that had carried dense communities were simplified. Landscapes that had held many kinds of animals now held only the ones that had found some narrow way through. It took time for those threads to thicken again. That is worth saying plainly. Recovery from the Great Dying was not a season of quick return. Marine ecosystems may have remained simplified for 10 million years or more. Life does not rebuild a world all at once. It begins wherever something can still live. One relationship becomes possible, then another depends on it, then another grows around both. Slowly, the empty spaces stop being empty. Slowly, an ecosystem remembers how to be complicated. Among the survivors were the archosaurs, the broad reptile group that would eventually give rise to crocodilians, pterosaurs, and dinosaurs. They were not the only animals rebuilding the Triassic world, but they had a set of traits that mattered in a damaged landscape. Their lungs were efficient. Their limbs sat more directly beneath the body than in many earlier reptiles, giving them a more upright stance and a better way to move across open ground. These may sound like small anatomical facts. In a world full of open niches, small advantages can become the shape of an age. The archosaurs were not one story. They were many experiments at once. Some were armoured, some were large predators, some belonged to the crocodile line branch and, for a long time, competed seriously with early dinosaurs. Others took to the air as pterosaurs, the first vertebrates to achieve powered flight. Their wings were not feathered, but membranes stretched across elongated fingers, a strange and elegant solution to the problem of leaving the ground. From a distance, the early Triassic would not have looked like the beginning of dinosaur dominance. It would have looked unsettled, different bodies testing different ways of surviving in a world still recovering from near collapse. The future was scattered among many shapes, and no shape yet knew it would matter more than another. The dinosaurs themselves appear in the fossil record around 230 to 240 million years ago. The first ones were modest by later standards, small, lightly built, often bipedal animals feeding on insects, small prey, and whatever else their bodies could manage. Nothing about them announced a future of giants. They were simply one lineage among others, viable but not inevitable. Then, around 201 million years ago, the world changed again. The Triassic-Jurassic extinction, probably linked to massive volcanic activity as the Atlantic began to open, removed many of the groups that had shared the land with early dinosaurs. Several competing archosaur lineages were reduced or vanished. Dinosaurs survived, and the space around them widened. That is often how dominance begins in the history of life, not as destiny, as survival plus opportunity. A lineage does not need to be superior in every possible world. It only has to survive the world that actually arrives. The Jurassic world that followed belongs to dinosaurs in a way that is difficult to overstate. Pangaea was breaking apart. New seas opened, climates shifted, places that had been dry became wetter. Forests of conifers, cycads, ginkgos, and ferns spread across landscapes that had once been harsher and more open. Into those recovering habitats, dinosaurs diversified with a range and confidence that still feels almost impossible when you remember where they began. Stand in a Jurassic forest for a moment, not a modern forest. No flowers yet, no broad-leaved canopy full of fruit and colour. The green is darker, older looking. Conifers, cycads, fern fronds, damp ground. The air is warm and wet. Insects move through the undergrowth. Somewhere above, an early bird-like animal calls, and beneath all of it, from time to time, there is a low pressure in the ground before there is a sound. The approach of something enormous moving through vegetation. Sauropods grew to sizes that still press against imagination. Brachiosaurus, Diplodocus, Apatosaurus, animals whose necks reached higher than most trees, whose footprints could become bowl-shaped depressions in mud and remain as fossils for more than 100 million years. Their lives were not slow-motion museum displays. They ate, moved, grew, reproduced, migrated perhaps, gathered perhaps, avoided danger when they were young, and became landscapes in motion when they were grown. Much about their physiology and behaviour is still debated, but the basic fact is enough. For tens of millions of years, Earth supported land animals larger than anything walking here now. Theropods diversified beside them, bipedal dinosaurs, many predatory, some small and quick, some eventually massive. And among the theropods something appears that changes the way the whole age should be imagined. Feathers, not flight at first. Feathers likely began as insulation, display, brooding material, or some combination of these. They were warmth and signal before they were wings. But once they existed, evolution had something new to work with. Across the Jurassic, some small feathered theropods developed bodies light enough, arms useful enough, and feathers arranged well enough that the air itself became a possibility. Archaeopteryx, found in Bavaria in the 19th century, and dating to roughly 150 million years ago, still has the power to unsettle categories. It had feathers and wings. It also had teeth, clawed fingers, and a long bony tail. It was not a clean boundary between dinosaur and bird. Boundaries in evolution are rarely clean. It was a living animal in the middle of a transformation, not knowing it represented one. Around it were other feathered experiments, some close to flight, some farther from it, some perhaps gliding, some running, some using feathers mostly for warmth or display. Evolution does not move along a single staircase. It spills outward, trying many versions of a thing at once, and only later do we look back and call one of those versions the path. By the Cretaceous, the dinosaurian world had been running for more than 100 million years. It was no longer a new world. It was old, established, inventive. Hadrosaurs moved across floodplains, some with hollow crests that may have carried calls over distance. Ceratopsians like Triceratops carried horns and frills, whose social meanings we still only partly understand. Small theropods show hints of complex behaviour and sensory lives far richer than the old image of dull, sluggish reptiles ever allowed. The dinosaurs were not monsters waiting for a movie camera. They were animals, alert, varied, social in some cases, strange in others, embedded in ecosystems as real and textured as any on Earth today. Some guarded nests, some moved in groups, some were prey for most of their lives before they were ever large enough to be dangerous. Their world included eggs, injuries, hunger, courtship, weather, seasons, and the ordinary vulnerability that belongs to any living body, no matter how enormous. That is easy to forget when a fossil reaches us as a skeleton in a museum hall. But the skeleton was once warm with motion. It had a morning. It had a last day. The oceans had their own reptilian age. Marine reptiles descended from land animals that returned to the water, became some of the most capable hunters the seas have held. Ichthyosaurs looked almost dolphin-like, streamlined and fast, with large eyes suited to deep water. Plesiosaurs moved on paddle-like limbs, some with long necks reaching through schools of fish. Later, mosasaurs, enormous marine lizards, ruled parts of the Cretaceous oceans. The sea that had once held only chemistry, then microbes, then the first small animals with eyes, now carried predators 12 meters long. Even the oceans had become familiar in an unsettling way, not because their animals were like ours, but because the roles were recognizable: hunter, prey, scavenger, nursery, migration route. The names would have been different. The logic was already there, and through all this, one branch of dinosaurs was changing in a way that never fully ended. The birds you hear outside your window are dinosaurs, not in a poetic sense, not as a metaphor. Their lineage runs directly back through theropod dinosaurs to the Jurassic. When the non-avian dinosaurs disappeared, the dinosaurs did not end, they narrowed. A branch survived, and that branch still wakes before sunrise, still crosses the sky, still fills the air on every continent. Then, in the Cretaceous, another transformation spread across the land, quieter than a dinosaur's footstep but just as consequential. Flowering plants appeared and diversified. Before them, terrestrial landscapes were dominated by conifers, cycads, ferns, and other plants that did not make the world look or smell the way it does now. With angiosperms came flowers, colour, scent, nectar, fruit, seeds packaged in new ways. Insects changed with them. Bees, beetles, moths, butterflies, wasps. each group shaped by flowers and shaping them in return. By the late Cretaceous, the land was no longer simply green. It was scented, it was coloured. It offered fruit, nectar, pollen, seeds. That may sound small beside sauropods and tyrannosaurs, but it changed the terms of life on land. The world began rewarding precision, the ability to find ripe fruit among leaves, to remember which plants fed you and which made you sick, to reach, pluck, smell, taste, and choose. It also changed time. Flowers bloom and vanish, fruits ripen and rot, pollinators arrive in seasons. To live well in such a world is to notice timing, colour, scent, return. The landscape was becoming more readable and more demanding long before there was a primate eye to read it. Long before any primate existed, flowering plants were preparing the kind of world primates would later need. A fruit held against green leaves, a hand reaching for it, eyes able to tell red from shadow. These things belong to a story that begins here, in the Cretaceous, while dinosaurs still move beneath the trees. The Age of Reptiles was not a waiting room for mammals. It was one of Earth's great worlds, abundant, layered, successful, and long-lived. It contained courtship and migration, hunger and sleep, nesting grounds, river crossings, droughts, injuries that healed, bodies that grew old if they were lucky enough to survive youth. It had ordinary days in it, more ordinary days than the whole span of human history by far. It simply was not our world. And then it ended. In the late Cretaceous, the world was full. Not full in one simple way. Full in the way an old ecosystem is full. Many roles, many dependencies, many lives leaning on other lives. Tyrannosaurs and their relatives held the top predator roles in the northern land masses, with senses and behaviour more complex than older images of them suggested. Hadrosaurs moved in herds across floodplains. Triceratops and its relatives grazed and defended themselves, with bodies built like arguments. Pterosaurs rode warm air above coasts. Birds were already diverse. In the seas, mosasaurs, sharks and ammonites moved through food webs that had taken tens of millions of years to elaborate. And in the leaf litter, in burrows, under roots, small mammals lived carefully. The late Cretaceous had lasted long enough to feel permanent if there had been a mind there capable of thinking in that way. That is one of the strange lessons of deep time. A world can be temporary and still last longer than any human imagination can easily hold. 80 million years is long enough for landscapes to become old, for lineages to rise and specialize, for animals to fit their surroundings so completely that the surroundings seem like the only possible world. The mammals in the undergrowth knew none of that. They were tuned to the close and immediate, the smell of a predator, the snap of a twig, the warmth of a burrow as evening cooled, the quick edible thing under a fallen leaf. Their bodies were made for margins. That would matter. 66 million years ago, a rock arrived from outside the Earth's ordinary cycles. It was roughly 10 to 15 kilometers across, moving at a speed beyond anything in lived experience. It struck what is now the Yucatan Peninsula, in shallow tropical water over carbonate and sulfate-rich rock. The impact vaporized part of the asteroid and part of the crust beneath it. Shock waves moved through the ground. Tsunamis radiated outward. Near the impact site, life ended in minutes. But the deeper disaster was not local. It was atmospheric. Sulfur aerosols rose into the upper atmosphere and reflected sunlight back into space. Fine dust and vaporized rock circled the globe. Debris thrown above the atmosphere fell back through it, heating as it returned, and wildfires spread across wide regions. Soot, ash, dust, and aerosols thickened the sky. The world dimmed. In that dimness, the temperature fell. More importantly, photosynthesis faltered. Not everywhere in the same hour, and not with the neatness of a diagram. A fern in one valley might survive longer than a forest on an exposed plain. Seeds could wait where leaves could not. Roots could hold life underground after the surface had failed. But across land and surface ocean, the organisms that turned sunlight into living energy began to fail. Once that happens, the collapse moves through everything that depends on them. Phytoplankton decline, then the animals that feed on them, then the fish and predators above them. Plants die back on land, then insects and herbivores, then the animals that hunted the herbivores. The largest bodies, the ones that needed the most continuous food, were suddenly the most vulnerable. Think about the sound of those years, not the moment of impact and that's too large to hear in any ordinary way. The years after, the kind of disaster that does not remain a single event, but becomes weather, hunger, darkness, failed nests, empty shorelines, and a sky that does not return to itself when it should. Calls across floodplains becoming fewer, forests thinning where trees died and no new canopy rose to replace them. The smell of ash in cold air. The slow absence of animals that had once made the landscape feel occupied. Not silence all at once. Something more unsettling. A world losing voices. The collapse took time, thousands of years, perhaps longer. But in the rocks it appears almost like a cut. Below the KPG boundary, non-avian dinosaurs. Above it, none. The ammonites, those spiral-shell survivors of previous catastrophes, vanished. Mosasaurs vanished. Many marine and terrestrial lineages vanished. Roughly 3/4 of Earth's species disappeared. The old world ended. That is the plainest way to say it. And because it was not our world, there is a temptation to hurry past the loss, to treat it as the necessary clearing of a stage, but that is too simple. What vanished had taken longer to make than our species has existed by an almost absurd measure. It didn't end in a single image. It ended as a sequence of absences. No hatchlings where there had been nests. No shadows of pterosaurs over certain coasts. No ammonite shells in seas where they had once been ordinary. No great herbivores crossing floodplains in numbers large enough to shape the vegetation. Extinction is often imagined as a moment of violence. Sometimes it is also a failure to return, and we should be careful about the story we tell next. The asteroid was not a gift to mammals. It was not arranged for us, or for anything like us. It destroyed far more than it opened. The world that ended was not a lesser world waiting to be cleared away. It was complete. It had its own depth, its own intelligence, its own long history of adaptation. It ended without meaning to. What survived did so because certain traits happened to work in the aftermath. Birds, the avian dinosaurs, were small enough, mobile enough, and flexible enough in diet that some lineages made it through. Some could live on seeds and insects that persisted after forests and food webs collapsed. Small mammals survived too, warm-blooded, burrowing or ground-dwelling, able to eat seeds, roots, insects, carrion, whatever remained. Their sensitivity to smell and hearing mattered in a dimmer world. Their small bodies needed less food than giant ones. Their burrows protected them from cold, heat, and exposure. And they had lived in margins for a very long time. For more than 100 million years, mammal ancestors had survived beneath the dinosaur world. Nocturnal, quick, cautious, adaptable. Under ordinary Cretaceous conditions, flexibility was not dominance, it was a way to persist. After the impact, flexibility became something else. A small animal that could eat many things, hide in many places, stay warm in a cold spell, and move when the light returned had a chance. The world after the impact winter was stripped down. Ash settled. The sun returned gradually. Plants regrew where they could. Insects found surviving niches. Birds moved through broken forests. Mammals came out of burrows into a landscape with more empty space than any mammal lineage had ever known. It would still take time. The first green after a fire is not a forest. The first survivor in an empty place is not yet a new world. But the direction had changed. The great bodies were gone. The margins were no longer only margins. Our distant ancestors were among them. Not impressive, not marked by destiny. Small, warm, watchful animals in the aftermath of a ruined world. They did not inherit the earth because the earth chose them. They were simply alive when room appeared. That is all evolution ever needs at first. Not greatness, not purpose, just a living body in a changed place, able to have offspring before the chance closes. In the tens of millions of years after the KPG extinction, mammals expanded. Not suddenly. Not like a door opening and everything rushing through at once. Mammals had existed since the Triassic. They had already spent more than 150 million years living mostly small, often nocturnal lives in a world dominated by other animals. In that long smallness they had gathered a different set of strengths. Warm bodies, milk, close parental care, sharp hearing, flexible jaws, teeth that could cut and grind different foods. None of these made them rulers of the dinosaur world. They made them persistent. The extinction did not create them. It changed the amount of space available to them. Over the Paleogene, from roughly 66 to 23 million years ago, mammal diversity spread into that space. Some lineages grew larger, some became predators, some specialized in grazing or browsing, some returned to the sea, their descendants becoming whales over millions of years. Mammals going back to the ocean from which the vertebrate line had come long before. Forests filled with plant eaters and the predators that followed them. Grasslands began to matter more in some regions. The basic outline of a world we would recognize was being assembled, slowly, unevenly, without knowing it was recognizable to anyone. Among the mammals moving through warm forested environments were the ancestors of primates. The fossil record is incomplete here, as it often is where we most want clarity. But somewhere around 60 to 55 million years ago, small arboreal mammals were developing a cluster of traits that would come to define primate life. Grasping hands and feet, nails rather than claws, forward-facing eyes, depth perception, greater reliance on vision, and a brain increasingly tuned to the demands of movement through branches. They were not almost human. They were not even close. They were small forest animals, more concerned with insects, fruit, warmth, danger, and one another than with any future waiting in their bones. None of these traits was aimed at humans. They were answers to trees. To move through a canopy, every branch has to be read. A hand reaches and tests the bark before weight follows. Fingers feel texture, thickness, the slight give of living wood. Eyes judge distance, not generally but exactly, because a small misjudgment can mean a fall. The body balances while the head turns, while another animal moves nearby, while leaves shift in the wind and light breaks into fragments. A primate does not only travel through a tree, it interprets it moment by moment with skin and muscle and eye. The tree canopy is an education that never stops. It trains without language. It teaches through consequences. A bad reach, a weak branch, a misread distance. Each one has a cost. A good grip, a remembered fruiting tree, a well-read warning call. Each one can carry a body one more day forward. Before the human hand held fire, it held branches. Claws are useful for many lives, but a grasping hand can close around a branch and adjust. Forward-facing eyes sacrifice some peripheral awareness, but they allow the two visual fields to overlap, giving the depth perception needed for reaching and leaping. Colour vision, in many primate lineages, made ripe fruit visible against leaves. A red or yellow fruit in a green canopy is not just beautiful, it is information. The forest trained the eye to notice it. And then there were other primates. A primate living in a group does not only watch branches, it watches faces. It notices who is near whom, who has moved away, who is tense, who has found food, who is safe to approach. This is not abstract thought yet. It is attention under pressure. In a social world, another animal's posture, gaze, and expression become part of the environment. You survive not only by reading trees, but by reading the beings moving through them with you. The primate face is unusually expressive. Small movements around the eyes and mouth can carry useful information: fear, threat, interest, appeasement, recognition. A primate that reads those signals well has an advantage. A primate that sends them clearly can alter what others do. Long before language, there was already a world of faces being read by other faces. A small turn of the head could matter. A sound from another animal could send the group upward through branches. A mother's body could be shelter, transportation, warmth, and instruction all at once. Learning did not begin in schools or around fires. It began in bodies near other bodies, copying, watching, correcting, remembering. This social attention matters because it is one of the roots of a later, more human capacity. The ability to imagine what another mind might know, want, fear, or intend. We're still far from that. But the architecture begins earlier than we like to think. Not in speech, not in philosophy, in bodies moving through trees, watching one another. There is also the old mammalian inheritance underneath all of this. For much of the age of dinosaurs, the ancestors of primates lived largely at night. Nocturnal life rewards acute hearing, refined smell, touch, and spatial memory. It teaches a body to navigate when the world is partial. When primates later became more active in daylight and vision expanded, they did not discard that older infrastructure. They layered sight on top of a nervous system already shaped by darkness. So the primate body became a meeting place of old adaptations. Mammalian warmth and care, nocturnal sensitivity, arboreal balance, grasping hands, forward-facing eyes, social attention. A body shaped not by one pressure, but by many layered histories, none of it uniquely human, all of it older than any human word. By around 35 to 30 million years ago, animals we would recognize as monkeys had appeared. By around 20 million years ago, the ape lineage had separated from the old world monkeys. Larger-bodied primates without tails, with more elaborate brains and social lives, living in forests that were themselves changing. Climate shifted. Forests became more seasonal in places, more fragmented, broken by grassland and open woodland. Some apes spent more time near the edge of trees and eventually on the ground. New ways of moving and feeding began to matter. The forest edge is its own kind of threshold, like the shoreline had been hundreds of millions of years earlier. Not water into land this time, but branch into open ground, shelter into exposure, old bodies into new problems. Among these apes were the ancestors of the great apes, and eventually of us. But we should not arrive too quickly. At this point in the story, there is not yet a human being. No one has made a stone tool, no one has carried fire, no one has buried the dead or painted an animal in the dark. There is a body, a particular kind of body shaped by old forests, hands that can grip and feel and manipulate, eyes that see in depth and colour, a nervous system trained by balance, touch, memory, and the movements of others, a social nature that treats attention itself as information. These are not uniquely human traits. They are primate traits, and they are old, far older than any tool, any fire, any word. The forest is very old. The body that learned to read it is older than we usually remember. Somewhere in that cooling, shifting world of the late Miocene and Pliocene, something was changing in certain apes, in how they moved, how they shared space, how they handled objects, how they watched one another. Too gradual to point to as a beginning. Too small at first to look like a revolution. The body was almost there. The mind that would ask the question had not quite arrived. The forest edges were where it began. Not in one place, not at one clean moment. Across millions of years, and across more than one lineage, some apes were spending more time away from the canopy, on the ground in open woodland, at the shifting margins where forest gave way to grassland and then folded back into trees. The climate of the late Miocene and Pliocene was changing. Forests that had covered much of Africa were retreating and fragmenting, opening more ground than before. Some ape lineages followed that opening. Bipedalism, walking upright on two legs, emerged in this unsettled world. It was not a neat transition, and it didn't happen for a single reason. Anatomy changed slowly. Wider hips, a different angle through the knee and ankle, a foot that stopped grasping and became a platform for carrying weight. The cost was real. Our skeleton still carries it. Backs hurt. Knees wear out. Childbirth became difficult in ways it is not for other primates. But upright walking freed the hands, and freed hands, in an animal already shaped by primate grip and colour vision, became one of the most consequential facts in the story. It changed perspective too. A body standing upright sees farther across grass, over shrubs, toward the movement of other bodies. It carries the head differently. It exposes the chest and face to others in the group. None of this makes a human yet, but it changes the relationship between body and world. The animal that once moved through branches was now learning a new geometry: horizon, distance, path, return. A hand no longer needed for locomotion can carry things. It can hold food while moving. It can carry an infant without stopping. It can pick up an object and turn it over, feel its weight, notice its edge. It can strike one rock against another and remember what happened. It can hold a sharpened stick, press a finger into wet clay, touch another body gently enough to soothe it. None of this is clever yet, not in the way we usually mean thought. It is curiosity expressed through the body, through touch, repetition, and the long accumulation of small encounters with the physical world. Over thousands of generations, some of those encounters began to leave things behind. The earliest known stone tools appear more than 3 million years ago, with some of the oldest examples found in East Africa. They are simple. One stone struck against another to create a sharp edge. But simple is not the same as small. A sharp edge can split bone for marrow. It can cut hide. It can process a carcass quickly before something larger arrives. What the first tools represent is not intelligence in the modern sense. It is attention, sustained, repeated attention to the relationship between an action and its result. That kind of attention is already a beginning. The hominins were not a single species. They were a set of related lineages, overlapping in time and space: Australopithecus, Homo habilis, Homo erectus, and others, each with different bodies, different ranges, different ways of living. Some coexisted. Some may have interacted. Some disappeared without leaving descendants. The human family tree is not a ladder. It is a branching, tangled thing, with broken lines and side paths we are still learning how to read. Homo erectus, appearing roughly 2 million years ago, was among the first hominins to move out of Africa in significant numbers, spreading across parts of Asia and Europe over hundreds of thousands of years. Their brains were larger than those of earlier hominins, their tools more standardized, their social lives probably more demanding. And they may have been among the first to use fire in a sustained way. Fire. The word deserves its own line because its importance is hard to see all at once. Fire made marginal climates more livable. It gave warmth, light, and some protection. It changed food. Cooking makes many plants and proteins easier to digest, releases more usable calories, and renders some dangerous foods safe. Some researchers have argued that cooking may have helped support the growth of larger brains by making digestion less costly. We cannot know the full relationship with certainty, but fire and increasing cognitive complexity appear together across long stretches of the hominin record, and it is difficult to imagine that connection meant nothing. Still, fire was more than technology. Before it was a tool, it was a place. A fire at night narrows the world to a circle of warmth and light. It draws bodies inward. It gives a group something shared to face. Around it, the day can continue after darkness has covered the ground. There is time that is not spent walking, cutting, carrying, or watching the edge of the trees for predators. Time to see the face across from you. Time for sound and gesture to become less immediate, less tied to a single warning or command. Time, perhaps, for the early forms of what would one day become language to stretch beyond the practical moment. Fire also changed the meaning of night. For most animals, darkness closes the world down. It narrows movement, increases risk, and hands the advantage to predators adapted for it. For hominins gathered around flame, night became partly inhabitable. Not safe exactly, never safe, but shared, bounded, lit from within. The first human worlds were not cities. They were circles of warmth in the dark. Language itself, or the long process that eventually became language, is almost impossible to locate in the fossil record. We have skulls that suggest certain anatomical capacities. We have tools and behaviours that imply communication, planning, teaching. But we do not have words in the rock. By the time Homo sapiens appeared, roughly 300,000 years ago in Africa, something was already in place that allowed for coordination and social cohesion on a scale earlier primates had not sustained. Whether that something was language as we would recognize it, or something approaching it, we cannot say precisely. We can say that it changed what memory could do. And Homo sapiens was not alone. Neanderthals lived across Europe and Western Asia, with their own tools, their own use of fire, their own evidence of care for the injured and sick, and possible burials of the dead. Denisovans lived across parts of Asia. Other lineages may still be waiting in the fossil record. The world of early Homo sapiens was not an empty stage. It was already occupied by other humans, related, different, and eventually gone, though not without leaving traces. Many people alive today carry small fractions of Neanderthal or Denisovan DNA. The molecular residue of encounters that took place tens of thousands of years ago. We are not as singular as we sometimes imagine. The Ice Ages shaped all of this. The Pleistocene, roughly 2.5 million to 12,000 years ago, was a time of repeated glaciations, when ice sheets expanded and retreated, coastlines shifted, populations were separated and reconnected, and routes across the land opened or closed depending on climate. Instability may have been one of the conditions that made human minds so flexible. A species that can live only in one kind of world is vulnerable when that world changes. A species that can track, adapt, communicate, plan, and cooperate across changing conditions has a different kind of resilience. The Ice Ages did not make us, but they were the weather inside which we became what we are. And somewhere in that long cold time before the last glaciers had finished retreating, people began to make images. We do not know exactly when this started, or where. We should not anchor the origin of symbolic behaviour only in the cave paintings of Europe, striking as they are. Ochre, a red pigment, appears at African sites that predate those famous paintings by tens of thousands of years. Shell ornaments, geometric engravings, and possible tally marks suggest that symbolic behaviour was older and more widespread than the chambers at Lascaux and Altamira. But the cave paintings are worth pausing on, because they are among the most direct windows we have into a mind close enough to ours that the distance almost hurts. In the firelight of those chambers, which would have flickered and made the painted animals seem to move, someone looked at a wall and saw an animal there, or imagined one into being. They prepared pigments, they returned to the same wall, sometimes across generations. They made something that was not there before. They made a bison from rock, colour, memory and desire. And then they left. The image stayed. A story is a way of carrying a moment past the moment it happened. The cave paintings have outlasted every word spoken in those chambers, every name, every language, and they still communicate across 40,000 years something simple and recognisable. Someone was here. Someone noticed. Someone wanted the noticing to last. The night sky was witnessed. The moon, whose slow drift away from Earth we noted at the beginning of this story, was now watched by creatures who kept time by it, marked its phases on bone, and built stories around its return. The same moon born from a catastrophic collision, the same moon that slowed Earth's spin and helped shape the tides, was now being looked at by something that wondered what it was. This is where the witness truly begins. Not at the first Cambrian eye, which saw but left no remembered world behind. Not at the first social primate reading another face across a branch. Here, in the circle of fire under the sky, in marks pressed into stone, here the world began, in a small and imperfect way, to be held in a mind that knew it was holding it. The last ice age drew to a close roughly 12,000 years ago. Glaciers retreated. Coastlines shifted as meltwater raised the seas. After 2.5 million years of repeated instability, the climate settled into something warmer and more consistent than the Pleistocene had offered. This mattered more than almost any single event in recent human history. The Holocene provided a pattern that could be learned, seasons returning in ways people could plan around, rains and dry months that could be remembered, seeds that could be planted with some expectation of what would follow. Not perfectly stable. There were droughts, floods, volcanic winters, local disasters, but stable enough for a different kind of human life to become possible. Agriculture emerged, not once, not in a single place, and not suddenly. It appeared independently in several regions over thousands of years, in the Fertile Crescent, in China, in parts of Africa and the Americas. People who had always gathered wild plants began favouring certain ones, clearing competitors, returning to the same places in the same seasons. Over generations, the plants changed in response to human selection, and humans changed in response to the plants. Wheat, rice, maize, these were not simply found. They were made slowly through accumulated choices no single person fully intended. The consequence was storage. Food could last beyond the day. Grain could sit in pots, then in granaries, then under the care of people whose work was counting, guarding, dividing, deciding. And where surplus accumulates, power accumulates around it. Who owns it? Who protects it? Who receives it when the rains fail? Villages formed around stored food. Towns formed around villages. Cities gathered around temples, markets, walls, and the administrative needs that surplus made necessary. The first great civilizations grew up in floodplains. The Nile, the Tigris and Euphrates, the Indus, the Yellow River, where the annual flood could destroy everything and also replenish the soil that fed everyone. This was not a simple improvement. Settled life brought density, disease, labour, hierarchy and dependence on harvests that could fail. It also brought continuity. The same wall repaired again, the same field planted again, the same dead buried near the living. A village is not only a place where people eat, it is a place where memory begins to gather in the ground. Writing appeared in several places as a way of keeping track. The earliest writing we have found is not poetry or myth. It is accounting, sheep, grain, debt, exchange, memory made external, marks on clay meaning that something had happened and should be remembered and could be checked later. Civilization is memory made external. Once memory could live outside the body in clay, stone, parchment, print, and eventually in digital form, it could accumulate in ways biological memory cannot. Knowledge did not have to be relearned from the beginning by every generation. One person's observation could become another person's starting point. Mathematics, astronomy, engineering, medicine, philosophy. None of these required only individual intelligence. They required accumulated thought. Recorded history fits into the last 12,000 years. On the deep time calendar we used at the beginning of this story, where 1 second is 140 years, the entire span of recorded civilization occupies less than 2 minutes. The pyramids, the Roman roads, the printing press, the Industrial Revolution, the Internet, all of it happens inside a brief disturbance in the rock record. And then, inside that brief disturbance, something happened that reached back hundreds of millions of years. We burned the coal, we drilled for oil, we extracted ancient carbon from buried forests, buried plankton, and seafloor sediments. Carbon that living things had taken immense spans of time to store away. We burned it for heat and light and motion, releasing in a few human generations what the planet had buried across geological time. When the first industrial furnaces were lit with coal, the carboniferous forests entered the air again, transformed, ancient, carrying in their bonds the stored work of sunlight. We became geological before we fully understood geology. A species that has existed for perhaps 300,000 years began, within the last 200, to alter the chemistry of the atmosphere, warm the ocean, move, species across continents, and leave signals that may remain legible in sediment long after the circumstances that produced them are gone. Future geologists, if any exist to read the layer, could recognize the boundary by synthetic compounds, changed isotopes, abrupt shifts in pollen, rearranged fossil assemblages. We will be in the rock, not as monuments or texts, but as chemistry, as a layer. We are not the first life to transform the atmosphere. Cyanobacteria did it. The Carboniferous forest did it. Life has always altered the conditions of the world it inhabits, and the world has always answered. But we may be the first to begin understanding the alteration while still carrying it out. The last second of Earth's year is the only second that has ever known what the rest of the year contained. Let the cities rest for a moment. The records, the arguments, the long noise of the recent past. Let them settle back into the final seconds of the year that has been running since January. Then look outward, into the time that remains. The planet is still in motion, with a future too long for us to picture clearly. It will not stop when we do, not when we are gone, not if we change into something we would not recognize, not even when the last descendant of anything we would call human is gone. The same forces that have been working since Earth formed are still working. The same slow processes, the same patient arithmetic. The continents will keep moving. Africa will continue pushing northward into Europe. India will drive farther into Asia. Australia will drift towards Southeast Asia. New mountains will rise from collisions. Old ones will erode back into the sea. The rock record will keep accumulating. Sediment, ash, chemical signals, the residues of whatever organisms are alive to leave them. The traces we leave will be buried, compressed, transformed into something the rock keeps but does not explain. What feels permanent to us will not survive in the form we know. Roads crack, towers fall, languages vanish, servers go dark. But the material disturbance remains. Concentrations of metal, plastic, concrete dust, changed soils, burned carbon. The future will not need our names to know that something happened here. Species will evolve and disappear. Birds alive today, living dinosaurs, descendants of Jurassic theropods, may give rise to forms no one can predict. Insects will continue their long experiment in adaptation. In the oceans, whatever lineages survive the stresses of the coming centuries will move into the ecological space around them. Life has always done this. It will do it again. The moon will continue drifting away. A few centimeters a year for as long as the system allows. In deep future time, the tides will be weaker, the day longer. The sky our descendants see, if there are descendants to see it, will be a different sky, with a moon smaller and more distant than the one we know. And the sun is aging, slowly. Stars do not change on human timescales, or even on the timescale of most species, but on geological time they do. The sun grows steadily brighter, roughly 1% every 100 million years or so. In perhaps 1 billion years, that added warmth may begin to overwhelm Earth's ability to regulate its temperature. The oceans may eventually evaporate. Photosynthesis may become impossible as carbon dioxide is drawn too low. Life may retreat, simplify, and eventually cease. Earth will have had its long habitable era, and that era will end, not suddenly, but gradually, the way so many endings in this story have come. And then, in perhaps 5 billion years, the sun will expand into its red giant phase. The rock that was once Earth, if Earth still exists as a distinct body, will no longer be a place of oceans, air, or weather. It will be geology in the deepest sense, rock and heat, whatever remains of a surface that once supported 4 billion years of life. None of this is a reason for despair. It is the scale of things. The same perspective that makes our lives feel small can also make them feel differently weighted, not less real, not less urgent, but held inside a much wider frame. We are not the first beings to live under a time limit. Everything that has ever lived has lived under one. The trilobites had 300 million years. The dinosaurs had 160 million. The cyanobacteria are still going. We do not know how long we have. What we know is this. For almost all of Earth's 4.5 billion years there was no witness. Mountains rose and wore down to sand with no eyes to see them. Oceans filled and emptied and filled again. Forests grew, fell and turned to stone. Life was busy, varied and world-altering. But it accumulated into no understanding of itself. That does not make the earlier world lesser. It may be the opposite. There is a kind of humility in remembering that beauty, complexity and consequence do not require an observer. The Earth did not become real when we arrived. It was already real, already ancient, already full of worlds that began and ended without us. Then something changed. Gradually, in a small social animal shaped by fire and ice, something appeared that could not only see, but remember. Not only react, but reflect. Not only survive, but ask. And so, For the first time in almost the whole span of Earth's history, the planet had something it had never had before, a part of itself that could look at the rest of it and wonder. We came from this planet. The iron in our blood was forged in stars that died before the sun was born. The chemistry in our bones is older than bones themselves. The oxygen-rich air we breathe began as a microbial byproduct in oceans without animals. The energy in our cells is processed by mitochondria, descended from once independent bacteria. We carry the Cambrian in our reflexes. We carry the forest canopy in our hands and eyes. We did not come to this story from outside it. We grew from it, from fire, water, oxygen, extinctions, and long, slow chemistry. We are one of the ways it continued. The planet didn't need us. It went on for nearly the whole of its history without a single witness, and it will go on after us, in forms we cannot predict, for longer than we can hold in mind. But for a brief time, this brief, strange, particular time, it has a part that knows it is here, a part that can trace the story of the fire that made it, the water that shaped it, the oxygen that filled its air, the forest that became its fuel, the extinctions that cleared the way, the hands that learned to grip and feel and eventually to write. To remember, here, does not mean to own the past. It means to receive it carefully, to understand that every breath, every hand, every thought, every city, every mistake, and every act of care belongs to a history much older than any human name. We are late enough to know some of it, and brief enough to know only a little. We are not the point of Earth's story, but we're the part of the story that learned how to remember. Let that hold for a moment. Wherever you are tonight, the sky above you is the same sky that once held no oxygen, then became breathable through organisms that never knew us. The moon above you, if it is out tonight, is still drifting, still gentling the tides, still marking the months the way it did for the first humans who looked up without knowing what it was. The ground beneath you is made from what was once ocean floor, once forest, once the body of something that lived and died and returned to the rock. You are the earth looking at itself, and now, for a little while, that is enough.